application sense network, and also then the probability statement, and then the algorithm itself. Also, some future work. Then I will wrap up the talk. So I would say sense network is not new anymore, at least to us. So everywhere involving data is sense network can find its applications, like habitat monitoring, intelligent environment, and inventory control. So this is a very straightforward example of the sense network being applied to a forest fire detection. So when the forest fire takes place, the source node, like in light blue, will detect the fire and will collect the data and transmit the data back to the sync node, which is in deep blue. So here our goal is to try to providing the long-lived, robust sensing service. But why we have this goal? Now let's look at the two problems we are having in current sense network applications. First, the error proneness of the individual node. So as we know, each sensor is very tiny and it's built in a very dense space, and it costs just like maybe pennies. So these nodes are very error prone, and plus they are working, usually they work in a very hostile environment, and no one is going to take care of once they are deployed. So one way we do to increase service reliability is we increase the density of the sensor nodes, so that as long we can keep a specific number of active nodes healthy, the whole network is running. So it could provide a service to the applications. And then we know these sensor nodes are driven by batteries, which only last like 4 months and at most 1 year. But we want these applications run like for years sometimes. So we want to prolong the lifetime of the whole network. So how do we do this to have a long lifetime out of the relatively short sense nodes? So currently the common practice is we only keep a minimal set of nodes active and turning off all the redundant nodes to conserve energy. And these nodes will take turn serving for the application, so that the lifetime of the whole network could be improved in the order of a couple times, depending on the density of the network. So a lot of work has been done in this area. Like Ascent is, I would say, is a pioneer work in this area. But the issue Ascent has is they have very frequent wake-ups, and the sleep interval is for the redundant nodes is fixed, which is not that dynamic, which is not adaptive to the dynamic environment. And also the Ps, I would say we kind of share the same goal as Ps. However, Ps don't provide a kind of tight, strict guarantee of the timely recovery, but well, we do. And also the OGDC. OGDC, I would say this is just a theoretical framework. It involves, their algorithms involve the heavy computation. However, they didn't consider random failures of the sensor node at all. So before I go into the details, let me introduce some key concepts which are vital for us to understand our algorithms. First, the sensing redundant set. So let's look at these table and graph separately. So here, this is a grid coverage model. Essentially, we virtually partition the network field into the grids, very regular grids, and each these green circles represent the nodes. So each node is supposed to cover some of the grid points in this network field. For example, for node A, it covers the grid 1, 2, 3, 4, and then node B covers grid 1, 2, 3, 4, 5. So this way, we can have the idea of the we can understand the sensing redundant set. So what is sensing redundant set? So for a node, its sensing redundant set is all its neighbors which have partially or completely coverage of the grid of the grid points. For example, we use A as example for the B, because B covers 1, 2, 3, 4, which are part of the A's grid list. So we say B is in node A's sensing redundant set, and it's the same. We can say the same to C. C covers 1, 2, 3, which grid 1, 2, 3, which are part of the grid list of node A. And then, so we could say node A's sensing redundant set consists of node B, C, D, E, F. And then we could also say redundant node always comes from the sensing redundant set, because they have some sort of overlap in terms of the coverage. Please feel free to interrupt me if you have problem understand my talk.
Excuse me, can you explain what is grid list?
The grid list is this is grid, and the grid list
Every
is
cell is a grid list, right?
no not every intersection of these lines.
Intersection.
So it's a grid list, a list of grids basically.
So can you give us an example, like for example, what is node A and why grid list is 1, 2, 3, 4?
You know what? I actually should have improved this slide much. This is why I said we should look at this slide separately. So as basically I just say, okay, this is node A, and this covers these 4 grids. So I just label it 1, 2, 3, 4. But actually in my simulation, I label the grid from bottom left to the top right, like 0, 1, 2, 3, 4, 5, and so. So it's.
But how do you know what it covers?
Pardon me?
How do you know what it covers? Like, how did you?
Oh, because we assume we know the sensing range, and we know the network field, the location of network field. So because we have and we also have the location of the node knows its own location. So
it covers something in a radius.
yeah, we suppose it's a regular disk model for the coverage. So that way we sort of know. I would say it's an approximation, but still it's the best that we can do at this stage. However, sensing redundancy is not enough for us, because usually when one active node dies, we need more than one redundant node to cover all the grid points the active node covers. The earlier work has shown that on average 3 to 5 nodes are needed to replace a node's sensing area. So in this case, we need 3 redundant nodes to cover this active node. When this active node dies, we need these 3 redundant nodes to wake up, to take over, to completely replace the active node. And this is only coverage-wise, and the communication-wise. You see, when node B dies, only the redundant nodes of this and this wake up. It could replace node B in terms of the communication between node A and node C. These nodes, even though they are the redundant nodes of node B, but they could not take over for the forwarding capacity between node A and node C. So from these two perspectives, we would say one redundant node is not enough to cover one active node. So with the concept of GAN, we would know the GAN is always from sensing redundant set. And now what we would like to do is we group the sensing redundant set members into GANs. So how do we do that? Here we know active nodes A is sensing B, C, D, E, F based on the coverage they have. And then we would say A's GAN list is B. CD, C and D, E, F. Why? So let's look at this. For node B alone, it covers grid 1, 2, 3, 4, 5, which is a superset of A's grid list. So we could say B alone could cover the node A completely. And for node C alone, we could not say the same, because node C doesn't cover the grid 4, which A covers. So we need the help of D, because D covers 4. So C and D combined could cover the coverage of node A. So C and D constitutes a GAN of node A, and then we could, following the same logic, we can say C and E is a GAN, D, F is a GAN. But here, but one thing we notice is since B is a GAN, BC actually is also a GAN to A. But obviously here B is redundant in terms of GAN. So we say we only consider minimal GAN, which means if any of the member of the GAN is missing, the remaining nodes will not be a GAN. So when we talk about the previous work, especially the P's, we said P's don't provide a up bound to timely recovery. However, we do. So our advantage is we provide a service loss time upbound, which we represent as delta. And our approach is the active nodes schedule their GANs to wake up, in turn serving as sentries or guards. So in this slide, we have like delta 300, and so the round, because in this slide the active node has 4 GANs. So we say the round is 4 times delta, and the active node makes a schedule like this. For the first GAN, it schedule it to wake up 1200, and the second GAN is scheduled to wake up delta after the wake up time of the first GAN, so which is 1500, and then the third GAN wakes up at 1800. So we can see from this axis, from this graph, we can see the wake up between 2 consecutive events is delta, and every round, which is 4 delta, again only wakes up once. So whenever the active node dies along this timeline, it could always be detected within delta. So are we good now?
Yeah.
Okay. So that's why we said we could statistically provide a outbound for timely recovery. So let's see what happens when the redundant nodes wake up. First, it will broadcast the probing message. And if the active node is still alive, it will receive the probing message and match the node ID with the GAN schedule table it already has, and then it will update the GAN schedule table by incrementing the wake up time by the round cycle, which is n times delta. Here n is the number of GANs, and then the active node will send back the updated schedule. But if the active node has failed, then the redundant node, the sentry, will not receive the reply message from the active node. Then the redundant nodes know the active node has died, so they will wake up to take over to recover the loss caused by the death of the active node. Now here one question. So far, do you see anything I didn't cover, any bug of this algorithm? Yeah, because the new active node actually knows nothing about its redundant nodes because it was previously in sleep and has not and it didn't have any way of knowing how its redundant nodes its GAN are doing. So here, the new redundant node should establish a schedule for its redundant nodes. So here, the new active node becomes active at 1200, and at that time, it has 3 GANs, and the GAN schedule table is just empty. And then, at time 1300, B wakes up, and B sends a probing message. So A receives it, and A searches its GAN table and knowing that B is a member of one of its GANs. So it will schedule the node B, schedule the GAN, including B, with B as a member to wake up at 1600. Because the delta is 300 and the B wakes up at 1300. So and in the counter it thinks, okay, I have only 1 GAN. So the next wake up time would be the current time plus the delta. And then at time 1400, C wakes up. And again, A would search its GAN schedule table. Okay, and A finds out that, okay, I already have a schedule for node C. So it still sends, and the current time is still less than the wake up time I have already scheduled for the node C. So I send the 1600 back to the node C, so that node C will wake up at 1600. And then at time 1500, node G will wake up. Okay, but because node G is not a GAN member of active node A, so A just ignores its message. And then this way, A could gradually fill up its own GAN schedule table and to have itself well protected.
So how do I know that who is my gang member?
Yeah, good question. So these at the very beginning of this algorithm, there will be an initialization period. In that period, every node exchanges information with its one-hop neighbors, including the location. So with that information and also with the coverage rate, with the sensing range, it would establish a GAN table for itself.
So that means people know where they are.
Yeah, people know where they are. Yeah. I believe even they don't have a chip like GPS. Still, there are some location algorithm we can use to find its own location.
And I have a question. So now in this slide is when the previous active node fails, right?
Yes.
So the gang which finds out earliest that active node has failed
Yes.
has to decide upon this next active node. So if there are 3 people in the gang which finds out that the previous active node has failed,
Yes.
which one knows that it's A and B and C? How does, any 3 of them can choose to be the active node, right?
Yeah.
So
Yes.
how would you choose among the 3 to decide who is A?
Yeah. So you see, this is a very good question because we know we need 3 nodes to totally cover the active node.
Okay.
So when the active node dies, we want all of these 3 to wake up.
Okay.
But this is just one of those
One
3.
of them, okay.
Yes.
And why are people waking up at 100 seconds when they're supposed to wake up at 300 seconds?
Which you mean?
So 1200, why is that they're waking up at 1300?
1300.
Yeah.
Oh, that's because you see B actually it's B actually follows the schedule for multiple active nodes.
Okay.
So there's
He
no
is waking up at some time.
yeah it could be scheduled by
Okay.
A or any active
Okay.
nodes which is in its neighbor. So here, because of the network dynamics, so the redundant node also will die before before it use up its energy. So let's see how we adjust the schedule table because of the failed redundant nodes. So here, at time 1000, D fails. And so then at time 1500, E wakes up. Here, we decided like we still want active node to wait like one more cycle to avoid that, to make sure like a D is really dead instead of it's just because of loss of the message or any other reason. And then when T is 2400, A still has not heard from D. Then A decides, okay, it's time to drop D from my gang list. So at that time, A cleans up its gang schedule table. So right here. And then the run then because the number of gangs changes from 3 to 2, so we change the run from 3 delta to 2 delta, and we do the adjusting accordingly when we make schedule for the gang which wakes up next time. So I guess this slide answers the question from you. So here, data structure. So initially, data structure initialization, graded list, neighbor list, SRS, sensitive redundant set, and GAN. And then we have a sort of distributed algorithm to select a minimal set of active nodes. Then the active node makes schedule for the redundant nodes. And then redundant nodes goes to sleep. And then after that, redundant nodes wake up as scheduled and probe. And this process will go on until we run out of nodes. So as we can see, we need actually a certain node density to have our algorithm work. And we actually initially we did our experiment on S2, but it turns out in S2 could not handle thousands of nodes in this kind of scenario. So we decided to build our own discrete event-driven simulator, and we just assume the link lossless link, and we don't consider details of the MAC layer. And here, this is the simulation setting. It's a 50 by 50 meter field, and the grid we make it as 1 by 1. So the typical node number is 600. And also because we want to take the random failure into account. So we designed some our failure model, which we call the catastrophic failure model. So in this model, a catastrophic event would happen with average period of FP, and at every event, average percent of F percentage node will die. So here the percentage is the percentage of the living nodes, excluding those nodes which has already been dead. And we use the performance matrix coverage ratio, which is the percentage of grid points covered, and the beta network lifetime. So this is the time the network lasts until the coverage ratio drops below beta and never comes back. And also the coverage loss time. So this is the duration for grid point from being lost to be recovered.
So that's failure period and failure percentage?
Yeah, this is a typo. This should be a failure percentage. Yes. So because we think we share our goal, our goal with P's, and the P's is kind of say our work in this area. So we compare our algorithm performance to P's. So here on the graph in the left, the x-axis is the time series, and the green curve represents the number of active nodes along the time, and the black curve represents the coverage, the change of coverage around the time. So we can see our algorithm always keep a steady number of active nodes when the simulation goes, and thanks to that, the coverage of the network could be maintained almost always above 90%. For P's, because P's only try to maintain a loosely time recovery time, so it doesn't have any deterministic or statistical guarantee to of a static number of active nodes, which we can see from this green curve. So obviously their coverage will be not as good as ours because there are not enough active nodes in this when the time goes on. And then the delta. So previously we said delta is a parameter in our algorithm. So let's see what happens when we change the delta. So here, when the delta goes up, our algorithm actually. So this the y-axis is the average coverage loss time. So when the delta goes up, so obviously the time between the interval between the consecutive wake ups of the gains increases. So the chances of active node deaths being detected would not be as responsive as a case with small delta. So when the delta increases, the coverage loss time just increases. But for the P's, because P's they have a similar parameter serving the same function as delta, but because they don't have any deterministic guarantee for coverage, so there's no kind of trend we can see from the P's.
Why is it going down?
Because it doesn't guarantee anything, so we cannot find any trend. It's possible they could go up next in the next point. So on the graph in the left, we can see when the delta increases, the lifetime, the 90% of the lifetime is still almost constant for our algorithm, and the P's, I would say, it's still very good. So it's there's a little bit of decrease.
What is 9% lifetime?
9% lifetime is, like I said, the beta lifetime. So the time the network lasts when the coverage is drops below 90% and never comes back.
And the nodes die because of other reasons on top of.
Yeah, it could be because there's no energy, because of any harsh environment events. And here we use the catastrophic failure model to simulate this kind of events.
So what is the failure period and failure percentage in these plots?
The failure percentage is I would say. So failure percentage is it's 5%, and the period is average lifetime of a redundant node, of a node, of idle node.
How much is that?
It's 4,000, 5,000.
Second.
Yeah, seconds.
How is that catastrophic?
Pardon me?
How is that catastrophic?
Because once it happens, you are not gonna survive.
4,000, 5,000 is a long time.
Yeah, but it's in Poisson distribution. Because we don't think like there's gonna be flooding like every day or every month. Flooding, it's right, but it's changeable. I mean, it's just we just use this 4,000 in this case.
And in your graph over here, right, how much energy is consumed by the nodes when they wake up and go back to sleep? On the right.
So currently, we only count the energy consumption of the packet exchange.
Okay.
So there are going to be a packet exchange upon wake up, and we count the number of packets, and I would say it's very. The energy consumption of a single wake up is very small compared to the energy consumption of the active node.
How well does that match with reality?
Pardon me?
How well does that match with reality? Because your percentage lifetime will go down if you periodically wake up, right?
Yes.
That's the trade-off you have over here. How
Yes.
often you wake up, and because you wake up periodically, you're going to sleep less often, which means you're going to trade off energy, right?
Yes.
So in order to provide for loss,
Yes.
you're actually reducing the lifetime of the network,
Yes.
right?
Yes.
So now is that number, the wake up, when the mode wakes up and goes back to sleep, is that like a really small number, or that's what you have assumed? But is a Berkeley mode when it wakes up and goes back to sleep, is that like a very, very small number, or?
You mean the wake up frequency?
No, the wake up energy.
Energy consumption?
Yeah.
We are doing some kind of experiments on the real modes, trying to find out
Okay.
what it really consumes. But again, this really depends on the density of the nodes around the neighborhood. If it's very dense, there's gonna be collision and much more packet exchange. So obviously, in that case, the energy consumption will be kind of high compared to the case with less node density. So it's in simulation we have to select some value we think is reasonable to get the result
So
reasonable.
how did you know that value was reasonable?
It's very hard to know. So that's why we are
You know.
yeah. That's why we are doing the experiment on the real time
Okay.
test bed. So back when I was implementing simulation, I didn't know.
Okay.
Right now I still don't know until the results goes up. But still, it depends on the scenario of the application, right? So. This graph shows the fault-tolerant capability of the R-Sentry. So here, this is the failure period. So we can see as the failure period goes up, which means as the failure frequency decreases, our algorithm could always, well, it's not. Is almost immune to the failure frequency in terms of the average cover loss time. But for P's, the average coverage loss time just goes up. And in this graph, when the 90% lifetime just goes up as the failure period increases, which is straightforward to us because when there are less failures, catastrophe events happening, the lifetime should be better. Any questions?
I'm done.
No. For this slide.
So I have a question.
Yes.
Are you considering a centralized network or distributed network?
Distributed network. This is a distributed algorithm because
Okay.
if we talk about centralized, there is a centralized because everything centralized upon the active node, but still this active node just only communicates with the node in one hop neighborhood.
Okay.
So-
Then I have a question. If node A want to sleep and he wants B to be active, but B also wants to go to sleep. Then how do you decide which node goes to sleep first?
Okay.
How do you negotiate with each other?
Yes. So like in the initializing period, we have kind of a random timer. So with a random timer, it's unlikely that A or B would make a decision at the same time. But once one of them make a decision, the other one will know the other node's decision. So this we have the tiebreak algorithm using the random timer. Okay, so here again, this is the failure percentage. So as the failure percentage increases, still our algorithm is good regarding the average coverage loss. And surprisingly, P is doing better. Why? Because with the failure percentage increasing, P has much shorter lifetime. So that's why its coverage loss time decreases here. But this doesn't mean P is better than ours because their lifetime is shorter, which can be seen from the plot on the right. This is the lifetime. This is the P's lifetime. This is R-Sentry's lifetime.
Can you tell me again what is average coverage loss time?
It's average time for a grid point to be recovered. For example, from time 0, the grid point the coverage is lost due to the death of active node A, and then 10 seconds later, A's gain wakes up.
So how is P going down?
Yeah, that's because in this case, P has shorter lifetime. Because at the end part of the lifetime, the coverage time is always bigger than in the early stage of the lifetime. Because R-Sentry has long lifetime, it experiences more scenarios when the coverage loss time is longer. Because at the end, at the later stage of the lifetime, there are less active nodes available, and the average coverage loss time will be longer compared to in the early stage. But for P's, because its lifetime is shorter, so it experiences less time in those.
So basically, your denominator here is causing it to fall, is what you're saying. Your average coverage loss time is the amount of time that it takes to cover up a hole,
Yes.
divided by the total network lifetime.
Yes. Yeah.
And since the total network lifetime is reducing, your average coverage loss time is reducing. Is that what you're saying?
Yeah. Actually, I didn't normalize this. So if I normalize this, you would see. I believe you would see a.
You should normalize.
Yeah. That's why I'm doing the talk to get feedback from you guys. Thank you. So scalability. So like you just mentioned, because as I answered, it's a distributed algorithm. So when the density of the node increases, R-Sentry is still doing good. It's still doing good here in terms of average service loss time, and in terms of lifetime, it's sort of linear, which is not imaginable in real world because, like I said, this is a simulation implementing as event-driven simulator. So a lot of overhead we failed to capture. But still it provides some hints, some idea how this algorithm works. So currently I'm working with Professor Ying Chang and my advisor, trying to find out what R-Sentry will do when some when there are some attacks from the active node. Like the active node could send some manipulated schedule to try to make redundant nodes to overactive or to oversleep. See how it affects the performance of R-Sentry and see what we can do to prevent this kind of attack. Okay, so future work. So one of the things we are trying to doing some experiment on the modes, trying to find out some reasonable values of the parameters we use in the simulation, and try to wrap up this project before I get out of here. So yeah, that's my talk. So any questions?